Hi, this is the CU Boulder 2020 capstone project for NASA JPL.
Hi everyone, before we start talking about the project, let's introduce the team members. Starting with me, I'm Nick LaMonica. I'm a senior in computer science this year, and I will be a developer and tester for the team.
Hi, I'm Willie Chu, developer and correspondent for the team.
My name is Austin Albert. I've been coding for almost 10 years, and I'm the Parspice project manager.
Hi, I'm Joel Courtney. I'm a physics and computer science major here at CU, and I'm a developer for this team.
My name is Joe Ledesma. I am a CS major, a developer, and a Q&A manager for the team.
Hi, I'm Matt Cohen. I'm from New Jersey, and I joined this group because I love space, and I thought it would be an awesome project to work on.
Hi, my name is Sahib. I do developing and testing for the team.
First, some background on our sponsor. JPL started as a group of Caltech students back in the 1930s. At the time, they were just hobbyist rocket enthusiasts, and it wasn't until the 1940s that they were adopted by the US Army and officially became Jet Propulsion Laboratory. During the 40s and 50s, JPL worked on rockets, missiles, guidance systems, and even satellites when we entered the space race. After they were transferred to NASA, JPL switched from working on rockets themselves to rocket payloads. Today, their mission is to carry out space and Earth science missions.
So here's just a quick overview of the current SPICE library, what it is and what it does. SPICE is a software library written and maintained by JPL. It can perform various geometric calculations in space, and these calculations include things such as looking at the current position of objects in space, as well as projecting future positions of different planets and spacecraft, as well as projecting geometric events in space. The most common uses of the SPICE library are things such as space mission planning, observation planning, and it's also used in data science and data analysis. SPICE was originally developed in the 80s, and its first use was in the Magellan mission to Venus that occurred between 1989 and 1994. Since then, it's been used in almost every NASA planetary science mission, and it's also used in plenty of other space organizations worldwide. And the cool thing about the SPICE library is that it's available online to anyone for free. It has wrappers in Fortran, C, Java, Python, MATLAB, IDL, and they also offer lessons for SPICE on their website.
So, why do we need a parallel SPICE implementation? The first is that the SPICE library is already flight proven and cannot be modified. This is because the SPICE library contains very complicated code that, when changed, might introduce bugs that will result in error-ridden data. The developers of the SPICE library have already decided not to change the SPICE library for this very reason. The second is that the SPICE library does not take advantage of current modern computing resources. Because the SPICE library uses global variables, that means it's not thread safe. And because it's not thread safe, that means that we can't run large batches or numbers of calculations using the SPICE library. So, our solution to this problem is to create a wrapper. This wrapper won't change the SPICE library in any way, but will also provide a way for the SPICE library to be called and be thread safe.
The objectives of Parspice are to allow GNI Spice jobs to be run concurrently without thread safety issues, increase performance of the implementation currently being used, performance benchmark tests comparing Parspice to native Spice, report and document implementation, and the use of Parspice. The initial approach our team took to parallelization was to use asynchronous messaging libraries to send packets of data back and forth between the client and parallel workers making Spice calls. The two frontrunners for our initial build were ZeroMQ and gRPC, of which the team came to the conclusion that gRPC provided the performance benefits we were after. Once we had a running Parspice implementation, we began to test it to look at the runtime and efficiency of the library. This was where we began to run into issues with the original design. It was inefficient, the messaging system overhead was at the point of packing and unpacking messages to be read and processed. This was unavoidable and with any messaging system, but seems to have been exacerbated in the case of pairing of Protobuf and gRPC. The Parspice implementation in its state at the time was several times slower than the native Spice implementation. Finding the break-even point would have required memory beyond our capabilities to find. So the wrapper library failed to meet the target objectives, so our team looked for ways to mitigate the problems and improve runtime. Ultimately, a better solution was found and implemented, of which will be explained here.
Our final design solves these problems by letting the user write their own code to run on the workers, instead of calling RPCs to do it for them. This has less network overhead and no messaging overhead, because we use socket streams directly instead of having a heavy library like gRPC. It uses much less memory, and now it doesn't care about Spice's internal behavior. Actually, if your job doesn't need Spice for anything, you don't even need Spice installed in order to use parspice. The biggest downside of the new design is that the build process is now more complicated for the user, but we've made some template projects available to the user to help them with that. Here's the basic design of parspice. The user writes the code that runs on the worker processes on the right and calls the run function on the main process on the left. Parspice runs the worker processes in separate JVM instances and starts up a list of servers, I server for input, O server for output. As the workers run, they receive inputs from the I servers and give outputs to the O servers, and at the end, parspice aggregates all of the outputs and returns them to the user. On that dashed line, the sender objects are what actually deal with the socket streams directly to send data between processes. If the user wants to send a primitive or an array of primitives, then we've provided pre-made sender implementations with the library. But if they have a more interesting type, like a class they've defined that they want to send between processes, then they'll have to make a custom sender implementation themselves. To measure parspice's performance, we've made a benchmark for the user to run on their computer. It records the runtimes of several different jobs with different computational overheads, different numbers of workers, different network overheads, etc., and tries to fit a small linear regression model to predict how long a job will need to run. We'll get into some actual performance comparisons in a bit, but generally, if that first coefficient in the model, the one that says 1.55, is less than 2, then parspice will perform better for almost any job, unless you have very large amounts of data to send between processes. After the model is fitted, it just does a bit of algebra and makes an estimate of the break-even point, which tells the user how much data they can send before using parspice makes their job run slower than it would have if they didn't use parspice.
So on this slide, we have performance results for two of the cases in our benchmark. We have the SIN CPT case as well as the output 1,000 integers case. Ideally, regardless of the amount of data sent or the computational cost per task, we'd like to see the runtime decrease proportionally to the workers, and we can see that in our red lines on the graphs here. These two cases show the extremes of parspice's performance. For the SIN CPT case, because it is an expensive task with a small output, it performs well and the performance improves as workers are added. However, for the output 1,000 integers case, because it is a cheap task with a large output, it performs horrible to begin with, and the performance is not improved in any meaningful way with the addition of workers. In both cases, the ideal red line was based on the direct single-threaded results without using parspice. The difference between these two cases can highlight for us why the break-even point is so important, as well as show us why a user should minimize the amount of data that they have to send.
Here are some use cases for parspice. Parspice works great for repeated function calls. This describes situations where large volume independent inputs are processed by a single segment of code. Parspice can be used to easily distribute the inputs among the workers to be processed concurrently. This should yield runtime improvements with the more workers used. Parspice can also speed up expensive function calls. The geometry finder functions in Spice are usually pretty time intensive when run on singly threaded applications. The function requires the input of a time frame. Parspice can be used to speed up such a function by splitting the call up into various time windows to be processed independently. The results from the workers can then be combined afterwards for a final result.
There are a few improvements that can be made to our implementation of parspice. The first would be improvements to the communication overhead. If ParseSpice was written in C, the inputs could be copied between processes, or the I/O could be sent through shared memory. Unfortunately, this is not currently possible on the JVM. The next improvements would be to make ParseSpice less restrictive and difficult for some jobs and job creation. Because the networking is hidden, it can make some jobs unnecessarily difficult to implement. It would be helpful for users if they could create their own full worker implementations. This would decrease user friendliness, but would remove possible restrictions in our implementation. And finally, there is no generic array sender superclass for users to send in custom types. Because Java does not let users create instances of arrays of generic types, it is not possible for a user to send in a custom type. It would be ideal to wrap custom types as a generic array with an inputted length, but sadly this is not possible due to limitations with Java. Overall, we have successfully created a solution for running SPICE computations concurrently, using multiple extra JVM worker processes where the user writes the code that runs on the worker. Improvements to the API or the communication overhead may be needed in the future, but our implementation as is should be a viable and sufficient solution for the vast majority of SPICE computation use cases.